Okay. All right, so subtracting the two equations, the y's have canceled. We have this huge operator acting on x. We're going to simplify it down algebraically. On the right-hand side, we're going to have to perform the operator on these two functions. So the left-hand side, we're just foiling out this set of binomials and then separately this set of binomials. Be careful of that negative sign there too. I'll go ahead and combine like terms while we're at it. Oh, I think I did it wrong. That looks better. Okay, so that's just simplifying down this algebraically. We still have to worry about the right-hand side of the equation. We have d plus 2 acting on e to the negative 2t. That's the derivative of e to the negative 2t, which is negative 2e to the negative 2t, plus 2 times e to the negative 2t. So those are going to cancel out. These probably will as well. So we have negative d acting on e to the 6t, which is the derivative. And then that's going to be a plus, because the double negative, 6e to the 6t. So it looks like they do cancel each other out. We're just going to get a 0 on that right-hand side. All right, is everybody with me? Any questions?
No, we're still following, or I am anyway. So for the right-hand side, I know you said you have to take the derivative.
Yeah. That's what this d tells us to take the derivative. So this says to take the derivative of e to the negative 2t, which is where this term comes from here.
Okay.
And then plus 2 times e to the negative 2t, which is the next term. So if you want to really think about it, this gave us this term, this gave us this term, this gave us this term, this gave us this term.
Okay, right. Tracking.
Okay. All right, so and then these all add up just to be 0, and then we're here. This is just changing it now back to differential equation form. X double prime plus 36x is equal to 0. Solve this the way that we always do. This is a homogeneous equation, so we're going to do auxiliary stuff. This has auxiliary r squared plus 36 is equal to 0, which has two solutions, plus and minus 6i. Which means that we're going to have the solution, this is for x. There's no real part, so there's not going to be an e. It's just going to be c1 cosine of the imaginary part, 6t, plus c2 sine of the imaginary part, 6t. Yep, everybody good with that? So that's going to be this one over here. c1 cosine, c2 sine. Okay. And now the same thing. Now that we have the x, we have to go back and solve for y. It does not look like any of these are super easy to solve for y, so we may have to do the same trick that we did before. Or what you could do, of course, is just start all over. So from here, instead of eliminating the y, you could have just eliminated the x's and solved for the y instead. Let's try to do the same trick we did last time, but without messing up. I'm just going to copy back the equations. All right, if you have x and you're trying to solve for y, it would be nice if we could get y on one side by itself and only x's on the other side. What I want to do is I want to eliminate this y derivative. To do that, we're going to subtract these equations. That way they'll just cancel out. So if I subtract the first equation by the second equation, I get this. And then the same thing, we want y by itself. So we'll get that negative 8y by itself first. Divide everything by that negative 8. Okay, and then if we just plug the x that I solved for here into these, that'll get the y by itself. To do that, though, we are going to need the derivative here. So, I don't know, just somewhere on scratch paper, just take the derivative. Okay, and then plugging that in. Y is going to be equal to 1/8 times this derivative here. And that's going to be minus 5/4 times the function itself. I know I'm cheating a little bit, copy pasting.
Yeah.
And then minus 1/8 e to the negative 2t plus 1/8 e to the 6t. Okay, then just combine like terms together, simplify stuff down. I might need some calculator help here. It's negative 3/4 minus 5/4 is 8/4, so negative 2c1. Oh, no, that's not right, because I did that on the... Oh, I don't think any of these combine together. Oh, this is going to be gross. All right, yeah, none of these combine together. So you're just kind of stuck with it. Hopefully if I type it in, it'll work though. Give me an hour. So negative 3/4 C1 sine of 16 plus 3/4 C2 cosine of 16 minus 5/4 C1 cosine 16 Whew, it worked. Okay. I feel like there's a better way of doing that, a little bit easier, and this would actually come out to be nicer looking. I'm not sure. Okay, but is there any questions about that one?
I don't think so. It's just a matter of, knowing when to do which process.
Yeah,
It's a lot to keep up with.
it is. I mean, it all comes down to the steps, and
Right.
So when you're handling the right side and you're doing is that the only time that you'll do the derivative, when you distribute?
if there's something on the right-hand side, you're going to have to do that.
That's the only time you'll do it, though, correct?
Yeah, if it's just zeros over here, you don't have to worry about it. Because anything acting on 0 still gives you 0. But if there's something over here, you're going to have to act on it.
Mm-hmm.
5.4 looks gross. I agree with you. Do we want to look at a 5.4 one before we go?
Sure.
Yeah.
Unless you want to extend the due date.
I know, right?
Not particularly. Okay, still have all day tomorrow.
Yeah.
All right, let's look at number 1 here. Verify that the pair x e to the 2t, y e to the t is a solution to the given system below. Sketch the trajectory of the given solution in the phase plane. No, Hayden, you cannot. So first things first is we just need to verify that these two things really are a solution to the system, and there's two different things here. So the first option, either the pair is a solution because in terms of the derivatives, in terms of x and y, x prime and y prime are blank, or the pair is the solution because in terms of t, the integrals are blank. In terms of x and y, the integrals are blank. That's kind of weird things to write out, I guess, but I think I'd have to be the first one. So these are going to be solutions because if I take the derivatives of the two pairs, it'll solve my differential equation here. So I think that's what they're asking you to do. So here they want you to take the derivatives in terms of t. If I look at x prime, that's just going to bring down that 2, so just e to the 2t. Y prime is just the derivative here, which is still just e to the t. What they want you to do next is they want you to rewrite these derivatives, but in terms of x's and y's. Basically, they want you to just write these down. Because 2e to the 2t for x prime is the same thing as 2 and then y, which is e to the t squared. So e to the 2t. So this is the same thing as 2y squared. And then y prime, which is e to the t, is the same thing as y. All right, so this is just kind of a crazy way of saying if you plug these in, you still get the same thing. That's why they're solutions. Does that make sense?
For the most part.
I think the problem is just in the way that they write out the question, but all this is really asking is if you plug these in, do they solve it? And yes, they do. All right, now it's asking us to sketch the trajectory of the given solution in the phase plane, and this can be kind of difficult. You want to think of your solutions, x and y's, as being ordered pairs with a parameter t. So this goes back to parametric equations that you saw back in Calc 2, 171 even. So just plug in different values of t and see what the ordered pairs do. So let's go back to our worksheet here. So we have x of t is e to the 2t, and y of t is just e to the t. So let's get a table with 3 columns, and we're just going to plug in different t values, and we're going to get different x and y values. Oops. All right, so my first column will be t's, my second x's, and my third column will be y's. So let's just start at 0. If I plug in t to be 0, x is going to be e to the 0, which is 1. Y is going to be e to the 0, which is 1. Okay? Let's plug in the next value of maybe 1. When t is 1, this is going to be e to the 2, which is some number. Does anybody have a calculator in front of them?
I do.
What's e squared? Just like 2 decimals.
7.389.
Okay. And then I need just e as is. I forget what that is.
That's 2.72.
Okay, cool. And maybe one more. Let's try 2. So now this is going to be e to the 2 times 2, so it's going to be e to the 4.
That gives us 54.59.
Okay. And then for y, plugging in t to be 2, it's just going to be e squared, which you already have. That's the 7.39. Okay. Cool. So just looking at these ordered pairs, what you'll notice is that the x increases dramatically. The y just kind of slowly exponentially increases. So we want to grab the thing over here that matches that. And the thing that I think that matches that is it's either the first one, A, or this one, D, where the x increases very, very quickly, the y increases relatively slowly. If I had to guess, I would say it's this one. Although, kind of looking at it now, and it might be this one. Don't forget that your calculator can graph parametric equations. So if you go into the calculator and change the mode to parameters. I wish I had a calculator here to show you, but I don't, sorry. So go into mode, and instead of function, change it to parametric. And then if you go into your y equals, it should give you x and y equations that you can plug in. So just plug in e to the 2t for the x and then e to the t for the y. All right, I'm picking this first one here, though. Okay, good. Whew. All right, so just to talk about it a little bit while you guys are fiddling with your calculators, is what this is mapping out is it's mapping out something that we call the trajectory of a system of equations. So if this system mapped out some kind of particle, this would be the path that the particle takes in this system.
That's pretty cool.
Yeah. And then, I mean, it doesn't have to just be like a path of a particle too. Like if this was representing, you remember the first example that we looked at in this stuff had to do with the, what was it, like salt water, and we had two different containers, container A and then container B. Same kind of thing. This would just be how quickly container A fills compared to how quickly container B fills. So here container A would fill up much quicker than container B, but every single ordered pair here would be the pairing of container A versus container B at that particular time as the trajectory takes its course. This will make a lot more sense in sections 5, 6, and 7 when you get into word problems. Then you can come back to this idea and kind of see how the phase plane helps us with these solutions. All right, this one was pretty quick though. We still got some time. You want to look at another one?
Sure.
Is there any questions about this one here? Number 1?
It seems pretty straightforward.
Okay. All right, question 2 then. This is more like what you guys are going to have to do here. So question 2 says to find the critical point set for the given system. And this is not as hard as it seems. So let me copy my system down. Okay. The critical points are just like they always have been in calculus. The critical points are where the derivatives are 0. So basically what we want is you just want to set your two equations equal to 0 and then figure out where the solutions to that are. I'm just double checking my notes to make sure I'm not saying anything crazy. Yes. Okay, cool. So yeah, all we're going to do is just anytime you see an x prime or a y prime, you're just going to substitute in a 0 for that. And now we want to solve this. And you want to figure out what ordered pairs solves both of these equations. And that's not an easy thing to solve for sometimes. I mean, sometimes it's very easy, sometimes it's not. This one can be a little bit difficult. Let's see what the best way to do this would be. I guess just substitution. So here, my first equation gives me x is equal to y. So then I'm going to substitute that into the second equation. That's going to give me, so this is going to be 9y squared plus 8y squared minus 7. We can add the 7 over and then combine the 9 and the 8 together. Divide. And then take the square root. Just be careful. Make sure you take the plus and the minus. But now that you know what the y is equal to, we get the x for free. Because remember that x was equal to y. For this example. That's not always going to be the case. And I think that's it. So every single combination of a possible x and a possible y are going to be the critical points over here. So use a comma to separate the answers, type an ordered pair. Okay, so I think there's going to be 4 of them. There's going to be the square root of 7/17, square root 7/17. There's also going to be negative square root 7/17 with positive square root 7/17. I don't know if you could just plug plus and minus in here. Should we try it? I'll try it for you guys. So I don't have to type that whole thing out. If I just do this. No, that didn't work. All right, let's see what the right answer is, just so I don't have to type it all out. I might have been goofed up somewhere. Is that just the same thing but fixed? Like if you multiply top and bottom by square root 17, does it give you that?
Yeah.
Okay. I see where my mistake was because I just said the wrong thing. Sorry. I said you would take every single combination of a plus and a minus, but you couldn't take every single combination. Because when x is positive, remember the y has to be the exact same thing. So the y also has to be positive. When the x is negative, the y also has to be negative. So you can't just do one positive, one negative, one positive. They're either both positive or they're both negative. I did have the right number.
So do you think it would take it if we plugged in like the square root of 7 over 17, or do you think we have to rationalize it?
No, I think they would take it
Okay.
the other way. It's just because just don't do the plus and minus thing like I did.
Okay.
Okay. So just to talk a little bit more about what that critical point actually does for us, let me get goofy here. So if I draw some stuff, so here's my ordered pairs. Oh, not my ordered pairs. Sorry, here's my my x and y axis. So square root 17 over 7, I have no idea what that is, but it's going to give us 2 points, right? It's going to give us a point here at the positives. It's going to give us a point here at the 2 negatives. Oops, down there.
It's about 1.5.
Okay, so 1.5, positive 1.5, negative 1.5, negative 1.5. So it's going to give us those 2 points. Your function, those trajectories are going to behave a certain way around these points, and it just depends on the system that you have. And there's a couple of identifiers out there, so I really want you guys to read through that entire section on your own to be able to see what those identifiers are. But your system's going to do something that behaves around this. Maybe it'll do something like this. So maybe it'll just be some kind of trajectory that you can kind of think of this like a gravitational point. Like it'll kind of come close to the system and go far away on both sides, like that. So your trajectories will do something like this. Okay, or what may happen based on that kind of system, just to redraw it, is maybe your system will be closed, and maybe it'll just be kind of, they'll be doing like tight circles around these 2 critical values. Whoop, not that, this. It just depends, right? I wish I had some time. I guess I have a little bit of time here. Let me pull up the book. Hopefully it'll pull up like real quick and on the first try. Come on, book. For whatever reason, whenever I'm in the meeting with you guys and I'm recording the screen, it takes a little bit longer. It's trying. And I gotta change the page though. Come on, book. Alright, we're in section 4. All right, we got something. I just got to get to the pictures now. So this is just, definitions and talking about how the phase planes work. A couple of cool definitions, time shifted and weird things like that. You kind of want to think of time shifted as being periodic, but in 2 dimensions instead. All right, promise, we're almost to the really cool pictures. We're getting there, right? So here's an example of one kind of field. Sometimes your critical points are going to be kind of like black holes. You can think of them like that. And every single trajectory is just going to dive in on that black hole and then just stop. So that's one kind. There's more, though. Here, this was kind of the one that I was trying to show you. So here you have like these, I don't know what you want to call these, like these weird hyperbolic type shapes where you have two critical values. No, this is just one critical value for this example. But here's the one critical value right in the middle. And then things just kind of dance around it. I don't know. Yeah. I'll be there in a minute. Sorry. Okay, and then there's like one really good set of pictures here. I just want to show you that, and then we'll go, here we go, I found it. Yeah. So here's all the different types of trajectories that you would get based on the different critical values. So a node, that's like the black hole thing. A spiral is kind of another black hole, but this time it spirals around. Or you can either spiral into it. This one's spiraling away from it. So here you have the saddle point kind of thing. That's those hyperbolic kind of weird things. They could be a center, either like a perfect circle, or these are ovals. That's the right word. What's the E term? Ellipses. Ellipses, thank you. Could not think of that word. This one's spiraling in, and then here we have, so this is just something that's unstable where everything's kind of blowing up and away from it. You can figure out what kind of critical value you have just based on your system of equations. And it's very easy to tell. It's just something that you would have to run through and see all the different cases. I just wanted to show you this picture though.
So what does it mean when it's stable versus unstable? I know we've talked about it before, but it's been a while.
Sure. You can kind of think of stable just using an example in one dimension. Okay. If we're talking about like an object that's falling, and we're talking about the terminal velocity. Terminal velocity is a stable equilibrium because anywhere you start, if you start out to be slower than terminal velocity or faster than terminal velocity, you'll eventually just reach terminal velocity. Gotcha. Okay. So it's stable. So it always goes toward that. Yeah, it's stable because no matter where you start, you go towards that equilibrium value. And then once you're at the equilibrium value, you're just there. Unstable would be the other way around. Unstable would be if you start anywhere close to it, you fly away from it. Okay, gotcha. Yeah. Okay, so I hope that helped with the homework questions. I think we've done pretty much. I've lost my homework. We've done pretty much everything there's to do on sections 2, 3, and 4 in the last couple of days. So finish this up today and tomorrow. Sections 5, 6, and 7, I only have the one homework on that, and I don't think there's very many questions in it. There is, yeah, there's like nothing at all. 4 questions. These are the word problems. There is electrical systems, that's the resistors and capacitor kind of things. There's the double spring systems, and then there's the my favorite section's the bio stuff. So I think there's even a section that I did on the susceptible, infected, that kind of thing.
Yeah, the epidemic graph.
Yeah, so there's some epidemic stuff in one of the videos. I think that's in section 5. Yeah, it's pretty pertinent and pretty cool based on everything that's going on. Okay, I have to go help my wife find something, so I'm going to head out.
Mr. Richard, I'm sorry, one thing. Could you just scroll up to your to the very beginning that I missed? I know you gotta go.
Yeah, sure can. I'll scroll through it real slow.
I just need to see what
Yeah, we just did another example similar to the one that you saw.
Okay, so you just multiplied everything through and then. Okay.
Yeah. I'm recording this, so I'll put this up on the thing.
Okay.
And you can
awesome.
filter through it then.
Thank you.
Yep, of course. Bye. See you.
Bye.
Remember Thursday, 6.
See you Thursday.
All right.
Yeah, have a good one.
You too.